Here's a pretty tricky problem for SHM for HL only, and it's to calculate the velocity of an object oscillating on a spring, a sort of mass on a spring, bouncing up and down, following the principles of SHM, where the acceleration of an object is proportional to the displacement but in the opposite direction. That is SHM. Here's the problem. Here's the problem. We've got an object, a mass on a spring, bouncing up and down with simple harmonic motion with frequency f. The distance between the extreme positions is y, the amplitudes, and the object at equilibrium is in position p. The question is, what is the speed of the object when it's halfway between p, its equilibrium position, and its extreme position? You have four possible options, so I suggest you pause the video and see if you can figure it out for yourself and let your brain go through a little neuroplasticity and figure it out. Otherwise, I'll crack on with the solution. Here we go. So if we've got to figure out the speed, it's going to be a little bit tricky. We're going to have to use this equation here. And this is essentially an algebra question, and just understanding how a lot of the equations can link together. First thing to notice is this equation is asking about velocity, and that's kind of where the plus minus comes in, because it might be going up, let's say it's positive is up, or it might be going down. But because there's no directions indicated and we're only asked for the speed, we can kind of ignore the plus minus there, which is useful. And if we look at all the options, they're all identical for the last three terms. We know that y comes from the problem, but that 2 pi f relates to omega, because omega, angular velocity or angular frequency, is equal to 2 pi f. So there's a bit of algebra to uncover here. So here it comes. The amplitudes are actually y divided by 2, because the amplitude is from the middle point P to the extreme ends, the extreme positions. So the amplitude is y over 2. That means when the object is halfway between the equilibrium point, it is y over 4. So that's very important. After that, it's mostly substitution and then a bit of algebra. So that omega has become 2 pi f. And these terms inside the radical have been substituted in. So x squared has become y over 2 squared. And then that's the maximum amplitude. And then x is y squared over 4 squared. Because we've got x squared here, and we've got to square this term. From there, it's mostly messing around inside the radical to give us some way of figuring out what happens to the proportions. So in equation number 2, the problem is something over 4, something over 16. We're going to, in equation 3, make the denominator both 16. That gives us 4y squared on the top as the numerator. And then when we take one away from the other, that gives us 3y squared over 16. You can kind of see where this is going now, maybe, which is equal to 3 squared, or sorry, the square root of 3. The y squared just becomes y, and then when we square 16, it becomes 4. Now, if you watch here, there's a 2 on the front, so if we divide everything by 2 there, we can cancel that 2 with the 4, and this gives us pi f root 3 times y over 2. The y could then drop down to the side here, and we're multiplying by root 3 over 2 multiplied by y. Rearranged, that gives us a. So there we go.